Now that we've practiced strong acids and strong bases, it's time for us to practice weak acids. So skills here, we're going to identify weak acids and bases. We're going to use ice charts to determine equilibrium concentrations and use that information to determine pH and relate Ka to pH. How does that even happen? Okay, so first question here is, what is the pH of 0.35 molar acetic acid? So again, we have a concentration, we have an acid name. You should know that acids like acetic acid, formic acid, those types of things are weak acids. So the first thing that you're supposed to do is find the Ka, and you can look this up in your book. And the Ka, sometimes it will be given to you in problems. Ka for this one is, 1.74 times 10 to the negative fifth. Okay. So, the next thing that we need to do is write out the reaction of what's happening here. So, we're taking these solutions in water, we're adding in acetic acid. Formula for acetic acid is CH3COOH. So this is the acid part. So that means this proton is going to be the proton that leaves. Because if we draw this out, it looks like this. And so this acid is very acidic. It has the lowest pKa on here. And that's what it's going to end up looking like. So here's the weak acid, here's its conjugate base. Okay, so we're taking water, we're taking our acid, CH3COOH. This works for any weak acid. And this reaction is of course going to be reversible because not 100% is going to make this product. That's what makes it a weak acid. Some portion of these protons will be lost, but some is going to remain. That's why it's weak. So the water is going to act as the base and pick up this acidic proton. So we're going to end up with H3O+. This is the same thing as H+, if you think about it. Okay. And then we're going to end up with our conjugate base, CH3COO-, because this proton has been lost. This was the acid, this is the base. Conjugate base, conjugate acid. Okay. Now, just like we did for the strong acids, ice chart. You're going to get really familiar with ice charts. Water does not have concentrations. Initial concentration here, 0.35 molar. Initial concentration of H+ is 0. Initial concentration of conjugate base is 0. We're going to change by some amount, we don't know how much. This is the difference between strong acids and weak acids. We don't know how much this is going to change. So we're using, you can use any letter you want, I use X. And we're going to gain over here by the same amount, so we use the same letter. And that gives us an equilibrium amount of 0.35 minus X molar. We're going to have X molar amount of H+ and X molar amount of the conjugate base here. Okay, so you can tell that this is already different than the strong acid problems. After the strong acids, we just take this concentration, plug it into the pH equation, and we're done. But now we don't know what the concentration of H+ is, and that's where these types of problems get a little tricky, and this is where you need the Ka. Okay, so the Ka is the dissociation constant. And so that is related to the concentration of the products. So that's our CH3COO- and the H+ over the concentration of the substrate. And water doesn't count because it doesn't have a concentration. CH3COOH. Okay, and we know all three of these values at equilibrium. And we know the value of Ka. It's listed up here. So we can plug in that we know that CH3COO-, the concentration is X. H+, the concentration is X. CH3COOH, concentration is 0.35 minus X molar. And all of this is equal to a value 1.74 times 10 to the negative fifth that you can look up in your book, online, wherever. On exams, of course, this will be given to you either in the problem or on a separate table. Okay, so now let's simplify this. 1.74 times 10 to the negative fifth equals x squared, because when you multiply you add the coefficients, you add the superscripts, and then over 0.35 minus x. Okay, so there's two ways to solve this. You can multiply and do the quadratic formula, or we can assume that because there is so much of this acid going in and it's a weak acid, a tiny fraction is actually going to dissociate. So we can assume that on the bottom part that this is negligible compared to this value. It's like adding one more drop of coffee to your cup of coffee, right? You wouldn't even notice. Or like adding one molecule of sugar to your cup of coffee. You wouldn't notice any sweetness. Or taking that away. You wouldn't notice any difference. So we can simplify this further. Top stays the same. But because this is so much larger than this x value, we can just assume that the major contribution is from the 0.35, the big concentration, and it loses so little that it doesn't matter. We can go back later and verify that this is indeed less than 5% of this value, if you'd like. So now we've got this equation, x squared over 0.35 equals 1.74 times 10 to the negative fifth. So then we can multiply both sides by 0.35 and we end up with x squared equals 1.74 times 10 to the negative fifth times 0.35. Okay. And then we're going to need to take the square root of each side. Okay, so we're going to end up with a value of x, and that's going to be the square root of whatever this value is. Oops. And it's going to end up being 2.46 times 10 to the negative third. And this is equal to the concentration of H+. So as you can see, there's a lot more work to not even get the answer yet, because this is just the concentration of H+ in solution. This is not the pH yet, because, as you remember, the pH equals the negative log of the concentration of H+, so it's going to be the negative log of that number. 2.46 times 10 to the negative third. Okay, and when we finally plug this in and you take the log first and then take the negative of that, then you get the answer. pH is 2.609. Remember, you add one more significant digit there because this is logs. And there you have it. Okay, the next question is very similar. What is the pH of a 1 molar solution of ammonium chloride, NH4Cl? Okay, and we're going to answer it in a very similar way. So first off, we're going to find the Ka. So the Ka value is 5.62 times 10 to the negative 10th. Again, this is in your book, this is online, this will be given to you on exams. Nobody has to memorize these. Okay, and so what's going on in this, we have ammonium chloride and it's going to be dissociating in solution. So another way that you can think about these is you can make the general form of an acid as HA. And you can ignore the contributions of water completely. So here we have HA. This is, if this is ammonium chloride, this will have a positive charge when the chloride is gone. So HA is going to dissociate to some degree to NH4 plus and Cl minus. Or sorry, H plus and NH3 and A minus. So we have NH4 plus, because we can ignore the chloride, is going to that one of these protons is going to leave, it's acidic, and we're going to be left with NH3. So this doesn't really look like a conjugate base, but it is. So this is just a simplified way of writing it. You can write the whole shebang, NH4Cl plus H2O is going to make NH3 plus Cl minus plus H2O plus H plus, but that seems like a lot of work, so this is the simplified version. Okay, and I just deleted that whole thing because we don't need it. This is so much more clear. Ammonium losing a proton. Okay. So again, we do the ice chart. Initial change equilibrium, because all of these pHs are measured at equilibrium. So the initial amount here is 1 molar. Initial amounts of products, there's nada, nothing. Again, weak, we don't know how much this is being converted to these. So we use X, use any letter that you like. So the equilibrium amount is going to be 1 minus X, and we've gained X's here. So this is kind of a little easier than the last one because we've just got 1 rather than 0.35. Okay, so again, now we know Ka is related to the concentration of H plus, concentration of A minus, concentrations of the products over the concentration of the substrate, Aj. Much easier to write this way. And then we plug those in, so we get x squared over 1 minus x, and we solve it exactly the same way as above. So you go ahead and try to remember those steps. And the final answer here, after you solve for x, pH equals 4.63. Okay, so go ahead and solve this problem and see if you get this exact same answer.